Hello, welcome back to the maintenance course. We are at lecture 3 and today we will talk a little bit more about non-repairables and how to analyze the repairability of such systems. So we have here the table of contents and we have a very busy schedule, let's say, where we have 6 topics and several subtopics of interest. Because this involves a little bit of probability theory and statistics knowledge, we will give a recap on section 2 and 3. We'll enter the advanced topics on section 4 and we will discuss some theoretical distributions. One of them that you probably already know is the normal distribution, and we will end up with the bathtub curve and the Weibull distribution. So now let us start with section 3.1, Introduction to Non-Repairables. I will try to answer essentially 3 questions. First, what are the assumptions that we need to make when we deal with a non-repairable system? Second, what is the big question that we're trying to answer? And what is the relevance of all of this? All of these topics will be covered in this section. So we have seen RAM analysis. We have discussed 3 or 4 methodologies of greater importance in RAM analysis for assessing reliability, which are, for example, the FMEA, the FMECA, the reliability block diagram, or the fault tree analysis. But there are other methodologies that are of interest, namely the non-repairable analysis and the repairable analysis. They don't have anything to do with RAM analysis, but they are a complement and a more quantitative way of establishing the reliability of a system. And in non-repairable analysis and in repairable analysis, we both resort to probability theory. So probability theory is very important to establish the analysis of both non-repairables and both repairables. Today we will discuss non-repairable systems, so we will talk about things such as the distributions that we can use to model the lifetime of an equipment and the bathtub curve. In the next lecture, we will focus more on repairables and we will focus on stochastic processes. But for now, let us stick to non-repairable analysis. Importantly, we need to make assumptions when we deal with non-repairable systems. One of the assumptions for this lecture is that whenever I'm talking about a system, I'm talking about a non-repairable system. So there's no concepts of time between failures or several failures of an equipment. There is only one lifetime, and that's the thing that I'm going to examine. The second property, or the second assumption, is that the systems are independent. So the behavior of one system, how a system behaves, is completely independent from the behavior of other systems. So if one failure happens, there is no connection to the failures of other systems. The third assumption has to do with the systems being identical. I can only examine properly non-repairables if the systems are identical, because I'm going to monitor systems in the past and I'm going to use that information to extrapolate to the future. So if the systems of the future are different from the systems of the past, I cannot make that extrapolation. So I need this assumption. It's a very important assumption. So in non-repairable analysis, something is given. You need data. You need data of how the equipment behaved in the past in order to answer the fundamental question. And the fundamental question is, when should you perform the maintenance of a future system? Where should you place the red line? So the red line represents a fixed time schedule, and that is what we define in non-repairable analysis using different methodologies, of course. But that is fundamentally the goal of non-repairable analysis. But why is this relevant? Why is this important? Well, it is very important because essentially maintenance and non-repairable analysis share the same goal. They want to find the best schedule for a system. And that is why we can use the methodologies of non-repairable analysis to produce the schedules of preventive maintenance. So again, let's talk about probability theory. Probability theory has several concepts of interest, such as the probability system, what is an experiment, what is a sample space. We will try to answer all of these questions and much more in this section. And we will start with a breath of fresh air, let's say, because we will start with the background and history of probability theory and how this all came together. We can attribute the interest in probability theory to the games of chance. So, for example, a poker game. A poker game is a game of chance, and when you play poker, you want to try to figure out the rules that govern the mechanics of the game. And that is what intrigued Pascal and Fermat in the 17th century, and what led to the formal developments in the field. Later on, other people contributed to the development of the field, such as, for instance, Bernoulli or Pascal, and we have the Prince of Mathematics helping a lot in the 20th century, Carl Gauss, and his brilliant mathematician skills helped provide, for example, information about the normal distribution and other things that he did. Nowadays, probability theory is applicable to many fields, so it has a general applicability, and the goals are usually three. First is to handle uncertainty, to make sure that we can handle something that is random, events that are random. But also it's important to analyze data, because we always look at the past data to try to project and to predict the future. And that is the third goal, to do prediction. But a fundamental, a stepping stone of probability theory is the probability system. And what is the probability system? Well, it's a fundamental concept, we already know that. And they define a random experiment. If you don't know what is a random experiment, I will explain in a bit. But essentially, a random experiment is defined by many components, by many elements. And one such element is, for instance, the sample space, the event space, and the probability function. And the probability system describes and defines all of these elements, all of these components. And so it is basically like an agglomerative of information to describe a random experiment. A random experiment is essentially a process that is repeated and that is controlled. We will explain what repeated and controlled means, but is where uncertainty lies, when we observe something that is uncertain. So every time that you hear the word uncertain or uncertainty, we know that we are dealing, or that we should deal with probability theory, with probabilities. And three examples of random experiments are, for example, rolling a dice. This is a textbook example, perhaps the most basic one. When you roll the dice, you don't know what you're gonna get. You just roll it and you see what you get. You can get 1 or you can get 2, whatever, but you don't know the outcome of your experiment. Then we have the example of the card deck. So if you take a card from a card deck, you usually don't know what you're gonna get, unless the cards are flipped. But imagine that they're not. You don't know which card you will get. And the final example is the example of an aircraft engine, in which it is an equipment that you are monitoring and that you don't know how long it will last. So it's also uncertain. A concept that is closely related to experiment is the concept of trial. Why? Because we talked about the experiment being repeated. So every time that you roll a dice, you're in a new trial. And a trial is essentially a performance, a realization of a random experiment. In maintenance, we also have the concept of trial. And basically a trial is an observation of an equipment until its end of life. So when we say that the experiment is a controlled process, what do we mean? We mean that it should respect three properties, the first one being reproducibility. So I should be able to do another trial in the same conditions as the trials in the past. And the trials should be independent, they should not affect each other. And there should be some predictability. So it should be able to have some kind of governing laws or rules that explain what is happening in the experiment. When we have an experiment, we have the concept of sample space associated. And what does this mean? It means that when I roll a dice, for example, I can get 1, or I can get 2, or I can get 3, or I can get 4, 5, and 6. All these numbers, from 1 to 6, are possible outcomes. It's the set of possibilities, and that is what we call the sample space. When we are analyzing a non-repairable equipment, what is the sample space typically? Well, the sample space is the number of positive real numbers, because it can happen any kind of number as long as it's positive. I cannot have a lifetime that is negative. So when I'm analyzing the time to failure, I can have any positive number in my sample space. So let's go into a little bit of formalism. So how do we define the sample space in mathematics? Well, it's the omega, and it's a set. That's why you have the brackets, the curly brackets. In the set, you have a W, and each W is an outcome. It's a possibility of something happening. So it's an elementary event. A metaphor that I like to think whenever I'm discussing sample space is a bottle of candy. And it's essentially each candy inside the bottle is an outcome, and the sample space is the entire bottle. So it's the entire set of little outcomes that we can get. But you heard me talk about elementary event, and you might think, what is an event? Well, event is simply a subset. So if you remember set theory, you have sets and you can have subsets. And since the sample space is a set, the event is just a subset. So it's a collection of elements that belong to the sample space. We can have elementary events, which are events of the sample space that only have one element, one outcome, or we can have events with several outcomes, and we can have events with no outcomes, which is the empty set. Sometimes we forget about the empty set, that he even exists, but he is always a part of any sample space. If the sample space belongs to a random experiment that is continuous, we're dealing with continuous numbers. And in that case, and it is also the example of maintenance, the events are a spectrum of numbers. So in this case, I can consider, for example, the event E, where it is from 1 year to 2 years and a half of possible time to failures. So the system can fail, or we are interested in knowing if the system will fail between 1 year and 2.5 years. So we have talked about events and sample space and experiments, but we didn't talk about probabilities, and the probabilities are the goal of probability theory. That's why it's called probability theory in the first place. So we need to develop methods to calculate probabilities. And where are the probabilities in our examples? Well, we care about the probabilities of the events. Okay, so we are always seeking to assign a probability, a likelihood of an event happening. So these two concepts are connected, the events and the probabilities. That's why we have to talk about probabilities. Before we talk about probabilities, we need to talk about events and sample space. If we have events and if we have probabilities, we know what is a probability. How can we map one to the other? Well, we have this thing called probability function, which is a mathematical function, of course, that is like a translator that calculates the likelihood of a given event in the sample space. There is this famous television show in Portugal where they have a Wheel of Fortune, and it's very popular, and people try to guess what's going to come out. And actually you can calculate the probabilities of each outcome coming out. So for instance, in this Wheel of Fortune, it is of course a simplification. You have an outcome that is more likely than the other two, and this changes the probability. So as you can see, we have a sample space of 3 elements, the 1, the 2, and the 3. And we have here the range of possible values for a probability, which is between 0 and 1. And then we have all the possible events. So we have the empty set, we have the set with 1, the set with 2, and then we have other sets of interest, namely the sample space, the 1, 2, 3. And these arrows that you see here are a representation of the probability function. So it's giving you a probability, it's mapping the event to the probability space. And for example, the empty set has a probability of 0. It will never happen because by definition the Wheel of Fortune will always give a result. But then you have the 1 and the 2 sets, which have a probability of 1/4, because if you slice the wheel into 4 pieces, you can make the calculation as so. And then you have the set with the 3, which has a higher probability, 1/2, and so on. And you have finally the sample space that has a likelihood of 1. Why? Because it says we are interested in either getting 1 or getting 2 or getting 3, and we know that it will either get 1 or get 2 or get 3. Probability functions are functions very special because they need to obey certain rules, certain axioms. One of them is the non-negativity. It means that the probability of A is always greater or equal to 0, so we can't have negative values as probabilities. And the normalization axiom says that the probability of the sample space equals to 1. Perhaps the most intriguing axiom is the additivity axiom. It says that if you have mutually exclusive events, events that do not share elements between them, you can add the union of the probability of the union of such events equals to the sum of the probabilities of each individual event. To summarize, we have again the concept of probability system. How do we formally define this mathematical framework for describing an experiment? Well, it's a W that is equal to a tuple, where you have the omega, which is the sample space, you have the F, which is the set of all possible events, and you have the P, which is the probability function. So when you want to define an experiment, you always need to know these 3 elements. We are now in section 3.3. We will discuss the topics of random variables, what is a random variable, and the topic of probability distributions. What is a probability distribution and how can we represent it? There are many ways to do so. We will see a few. A random variable is kind of like a tricky concept because we might think that we don't really need it, and it's a mathematical formalism more than anything. But it comes from the need to give names to categorical values. So when you have an outcome of an experiment that is categorical, that is not a number, you need somehow to translate that into a number and then to assign a probability to it. And that is basically a random variable. But since we do it for categorical values, we also need to do it for numerical ones. So this concept of random variable is pervasive through all experiments in probability theory. As I said, it's difficult to describe or to explain why we need a random variable in the first place. Why don't we just use the outcomes and transform them into probabilities directly? But I guess they are the nouns, the numerical nouns of probability theory, because in mathematics we need to give things a name. And that name that we are giving, that mapping, is a function that we call random variable. Because we are transforming outcomes into numbers in the real line, we can have two types of random variable, the discrete and the continuous. And according if it's discrete or continuous, the methodologies that go with it are completely different. But if it is discrete, if the range of the variable, if the sample space is countable or finite. So for example, if we are dealing with the integer numbers, the random variable is continuous if the range of the variable, if the sample space is measurable, so if it has infinite possibilities. So it's a sample space that is infinitive, that is a spectrum of numbers. So let us see things in formal terms. So you can have an event, and an event is just a collection of outcomes, and you can say that the random variable applied to each outcome gives an x, a small x, which is the name, or as we might call it, the translation of the outcome, but it represents the outcome. So there is always this one-to-one connection. And then we have the probability, which we can calculate as the probability of E, but that is the same as saying the probability of x being equal to x. And that is another, we use the same p, but it's not just a probability, but it's not the probability function, it is the probability distribution function, because now we are dealing with a random variable, with a translation. So we have these two similar ideas, the probability function and the probability distribution function. What is the difference? The probability distribution function comes from the random variable values in the real line, and in turn the domain of the probability function are the outcomes itself, so before the random variable is applied. So it's essentially the probability distribution, it's basically the table that is shown here. So it correlates the x of n with the probabilities that are given by the probability function. The probability distribution function can be described by a table, at least in the case of discrete random variables. But once we have a big sample space, we have to do something about it, and we have to visually describe the function using other representations, such as, for instance, the probability mass function, which only works for discrete random variables, the probability density function, which only works for continuous random variables, and the cumulative distribution function, which is the same for both the PMF and the PDF. And we have also summary measures, such as, for instance, the calculation of the expected value or of the standard deviation. A probability mass function is a representation of the probability distribution function of a discrete random variable, and it shows immediately the probabilities. That's the beauty of the probability mass function. You just look at the graph, at the visual representation, and you can see, for example, that the 1 has a probability of 0.2, or that the 3 has a probability of 0.5. It's really easy to analyze and to interpret just by looking at the chart. A probability density function applies to continuous random variables, and it's a little bit more tricky because the probability is not the density. In the y-axis you show the density, which is not the probability. So you cannot say that, for instance, in -1 you have a probability of 0.2. That's not the case. To get the probability you need to integrate, and you can only get the probability in an interval, so from -1 to 0 or from 0 to 1. You integrate that area under the curve and then you get the probability. As I have said, there is a difference between the representation of the probability distribution function according to if the random variable is discrete or non-discrete. So here on the left you have a discrete random variable. It assumes values like 1, 3 and 7, and which is a finite set in this case, and you can represent it with a probability mass function. But in the case of a continuous random variable, such as the one that I show in the right, which assumes values in a spectrum of numbers, you have to use the probability density function, which is more tricky to get the probability. We are now finally entering the world of reliability theory, and I think the four concepts more important are the time to failure, the failure or reliability function, and the hazard function, and we'll discuss it now. So it's going to be an interesting section. We have touched this topic already because you have seen the importance of monitoring past equipment to figure out the red line, the maintenance hard time event. But let's give this a name, and we call this time to failure approach. In a time to failure approach, we have four things that we need to define, because essentially we are defining a probability system. And the first thing that we need to define is what are we going to examine, what are we going to monitor, and it is essentially the time to failure of a groups of equipment. So we are interested in knowing how long they last. The random variable is the time to failure, the TTF, that I will talk extensively, and the outcome is a specific value of the time to failure. It's a specific time that the system can last, being that named X. And then we have the probability distribution function, which we represent by the probability density function that will define the random variable time to failure. Okay, so importantly, we need to check how we measure the time to failure. This is a little parenthesis in our story. But when we have a time to failure, we are monitoring several systems. We need to measure this time to failure. And how can we measure it? There are different measures, such as usage measures or calendar time measures. So for instance, the number of cycles of an engine is an usage measure, while the number of days until a jet engine overhaul, it's calendar time. So you have to choose according to your application and to your expectations how to measure the time to failure. So when you have a probability density function of a time to failure random variable, you can have something like this with this shape. It could be different, of course. But how do you figure out what's the probability of having a time to failure between 0 and 3, for example? In this case, this is the integral of the probability density function from 0 to 3. So that's how you capture the probabilities of failure happening. You integrate between the intervals of between the boundaries of the interval that you are interested in. So we have this concept, which is the failure function, and it is nothing more the integral to the left of the probability density function. So it covers everything from the time t until 0. Why 0 and not minus infinitive? Because of course we don't have time to failures that go negative. So it has to start at 0, because it is essentially the probability that a failure will occur before or at time x, making no sense to calculate probabilities of failures before time 0. Now visualizing the failure function, we can see here that the visual representation of a failure function at time 3. So all the black shape is the probability that the failure occurs before or at time 3. So you see here a probability density function and a failure function, and the failure function is obtained by integrating until that point the probability density function. And importantly, we see this shape of the failure function, which could be different because it varies according to the shape of the probability density function. But you can see that it's always an increasing function because it's a cumulative function. It's accumulating the areas, so it always has to be a growing function. Let us check now 3 visual properties of the failure function. And one thing is that the failure function at infinitive equals to 1. This is because the integral from 0 to infinitive of the probability density function equals to 1. If you remember the axiom of normalization, this has to do with the fact that the probability of the sample space equals to 1. A second property has to do with the relationship between the probability density function and the failure function, and it says that the failure function at a given time equals the integral of the probability density function from 0 to that time. We have been talking about the interval of 0 to x, but what if we wanted to calculate the probability of the time to failure being in an interval from a to b? In that case, you have to subtract the failure function at a from the failure function at b. And this is essentially the integral or the area under the curve between the boundary a and the boundary b. This is basically a summary of the failure function properties that we've discussed. We have here the formal definition of the failure function, and it relates to a probability. It is a probability that the item will fail in a given interval from 0 to x, and it is also the integral or the area under the curve of the probability density function to the left of the time x. Importantly, when we talk about failure function, we talk about cumulative distribution function. It's the same idea, but we just give it the name of failure function in reliability theory. If we're curious about the time to failure belonging to an interval, we have to subtract the probabilities at the boundaries, which is the same as subtracting the failure functions at the boundaries. The reliability or the survival function, we can also call it survival function, is a function that it has a lot to do with the failure function because it's the inverse, and it's essentially the likelihood that the equipment will survive in the interval of 0 to x. So instead of thinking about the area to the left, we will think about the area to the right of the probability density function. Formally, the reliability function is as if it is represented here, and it is the probability, like we said, that the failure will not occur before or at time x. So it's the probability that the time to failure will be before x, and that is essentially to calculate the integral from x to infinitive of the probability density function. So essentially we have to cover the area to the right of the value x to obtain the reliability function. Remember from the normalization axiom that the sample space has a probability of 1. So that is also the case for the probability density function. The area under the curve equals to 1. So the reliability at time x plus the failure function at time x has to be equal to 1. A summary of the properties of the reliability function. We have here the formal definition of the reliability function, and it is essentially the probability that the time to failure, that the item will not fail in 0 to x, so it will survive at least to time x. That's why we don't have greater or equal, we have just greater. And it is 1 minus f of x, so it's the inverse of the failure function, and it's calculated as the integral to the right of x of the probability density function. It is also called the survival function of the item. There is this pressing question in maintenance that we want to know if we have a system and it's functioning, it has functioned for a long time, and we want to know if it fails. And failure function and reliability function do not necessarily cover this question. Why? Because the failure function is the probability that the system will fail until time x, and the reliability is the probability that the system will survive until time x. And this is different from saying that my system, what's the probability of it surviving a little bit more given that it has survived so far. So we are talking about conditional probabilities here. The function that answers this question is the failure rate, or the hazard function, and it is basically defined as a conditional probability and the limit of that conditional probability. So I'm considering a very small time interval, and I'm saying, is it going to fail immediately now in this very tiny interval, given that it has survived, given that the TTF, the time to failure, is bigger than x, so it will it has survived until now. Will it fail immediately? That's the question. And you have here several formulas that show how you can move from one function to the other, from the probability density function to the failure function, or from the reliability function to the failure function, and so on. We are now at the 5th section, and we are going to talk about distributions. Distributions, namely the exponential, the lognormal, and the normal distribution. What is essentially a distribution? Well, a distribution is a group, a collection of probability density functions that behave in a similar way, whose probability density function and consequent functions are governed by a certain equation. And this is an example of a normal distribution. Importantly, the normal distribution always follows this type of shape, this bell curve, and this is what distinguishes the normal distribution. But it could have a different shape, it could have a different form, and that's what we are going to see today. We have here the log-normal distribution with a mean of 2 and a standard deviation of 0.5. You can see the probability density function at the top, at the right top. And you can see that the probability density function has a curious shape. But more importantly, we should look at the hazard function. And the hazard function is a decreasing function after some time. And this will be very useful because it will allow us to monitor, to model burn-in failures periods. Burn-in failures you typically happen at the beginning of the lifetime of an equipment, and it's also called the infant mortality region, the debugging region. Why do we call it debugging? Because usually you can do some burn-in testing to avoid these types of failures from happening with the client, or it's called also the burn-in period for the same reason. Reasons for failures at this stage, at the beginning of the lifetime of the equipment are, for example, manufacturing and design problems. And it's essentially, it always has the same shape in terms of hazard. You have more risk at the top and then increasingly less risk of failing. So we have at the beginning a very high likelihood of failing. And then you have the exponential distribution here with the lambda of 4. It means that the probability density function is going to start at 4, and it's going to have a hazard function of 4 also. Okay, so the lambda is very important, and it's described in the failure density function at the bottom right. Importantly, you can see that the hazard function is constant, which means that it can cover the period of random failures that is perhaps the longest period of the lifetime of a family of equipments. And the random failure period or constant hazard it typically happens after the infant mortality or the burn-in period, and it's a period of equal risk of failing, given that the system has survived so far. So failures will occur randomly in this region, and they're usually caused by random overstress, not caused by aging or by any time influence. Finally, I would like to talk about the normal distribution. This distribution is well suited to for wear-out failures, for failures due to some kind of wear. And it has always this bell-shaped curve, the probability density function, and the hazard is increasing, so the risk is increasing over time. And for that reason, we can use it to apply to wear-out failures, where in the wear-out failures is basically a region after the random failure period, where wear, erosion, corrosion, and even fatigue can accumulated degradation essentially can cause a failure, and the risk is increasing with time. Let us now enter the 3.4 section, Weibull distribution and bathtub curve. The bathtub curve is a central idea of reliability theory that states that an equipment will go through a series of failures throughout its lifetime, and they follow a shape. They follow the shape of bathtub curve. So in the beginning, a lot of equipment will fail due to infant mortality, and then or manufacturing defects, and then we have a period of random failures, and in the end the risk is increasing, so more and more equipment of the surviving ones will fail due to wear-out failures. So the reliability of most products follow this bathtub curve. And it would be important that we could cover all the 3 stages with a single distribution. Wouldn't it be great? So, and it's actually possible because we have the concept of Weibull distribution that allows us to do so. So we have here formally the Weibull distribution. We have this expression, a very big one, but the important is the 3 parameters, the shape, the scale, and the location. The location is not so important because essentially we always locate the Weibull distribution at 0. So we can work with this shorter version. If we set the location to 0, we reduce the equation and we have this more easier to handle equation. The beta is perhaps the most important parameter because it's going to set how the hazard function will look like. So you can have different values of beta, and we will see how this affects the hazard function. Of course it affects the probability density function, but it also affects the hazard function. And if you set the beta between 0 and 1, you are in a period of burning. If you set the beta to 1, you are always in a period of random failures, and if you set it to a value bigger than 1, larger than 1, you are in a wear out period. So it's really useful to use this distribution because we can parameterize it and we can get different hazards out of it. So we can cover the bathtub curve completely. We can also vary the scale, and essentially it doesn't change the shape of the probability density function, but it changes the range of numbers that it covers, the sample space. A final result that I would like to discuss is what happens when the failure function is set at the scale parameter. And the scale parameter, as you will see, is the time at which 63.2% of all the equipment will fail. So when you're defining your Weibull distribution, you immediately define the what we call the characteristic life. Now that we have covered the basics of reliability theory for non-repairables, I would like to thank you for being with us and thank you for watching. See you next video.